Hello ROS developers, and welcome to a new video on how to develop with ROS. If you want to learn anything about ROS, this is your channel. ROS navigation, ROS with drones, ROS for autonomous cars, everything ROS is here. Learn ROS step by step and push your ROS learning with just 10 minutes of video. Hi, I'm Arif, and today we are going to answer this question about how to rotate a desired degree using feedback from odometry. Before we start, remember to visit the Robot Ignite Academy, our online academy, where you will find practical online ROS courses using simulated robots. No installation is required. You will find the link to the academy on the video description below. Now let's start with the ROS answers, with the question on ROS answers. So how to rotate a desired degree using feedback from odometry? Can I send a desired angle as a parameter to the program, and when I run the script, it automatically rotates a desired degree using feedback from odometry? I have odom topic. Okay, I have odom topic, and my script gives me an angle which the robot have to rotate. So I want to control the degree of rotation using angular velocity from odometry. This is possible. Okay, this was asked by Abdul Karim. There is a comment here saying that this question is too vague. What is the program? What is the hardware setup? And so on and so forth. Um, yeah, we don't have all that information, but I think we can get the general idea. The asker, the original poster wanted to rotate his robot to a certain degree, um, and using feedback from odometry, as well as telling the robot to move using angular velocity, probably command vel. Okay, so let's try this, and as usual I will be using our ROS development studio, ROS DS. So let's create a new ROS project. Let's name it rotate robot, something simple. Create new project, new ROS project. Okay, so once your project is created, let's open it up. Open project. And then you say no there. Alright, so what do we need? We need, of course, a shell. Okay, let's start with opening up a simulation. Let's get a robot up. Let's just go with Turtlebot 2. This is something that I suppose most of us are familiar with Turtlebot, and it does have the topics that we require. It we control, we give commands to it using command vel, and we get uh, odom topic as well. Okay, so while that is loading, we have uh, a shell as well as an IDE. Okay, so um, okay, our robot is there. First thing, let's try and see what information that we are getting from odom topic. Okay, so run ROS topic list. Okay, just to see that yes, we do have odom topic as well as command vel. Alright, we are going to use these two topics today in this video. And then let's do ROS topic echo odom. And I'm going to open up another shell. Okay, this is the um, messages that we're getting on odom topic. Okay, on the other shell, what I'm going to do is I'm going to ROS run teleop twist keyboard. Teleop twist keyboard is a node that we can use to send messages to command vel. So for all robots that subscribes to command val, we will be able to control the robot using this particular node. Okay, and we can control the robot using our keyboard. So it says reading from the keyboard and publishing to twist. So to move around, we press I to go forward, K to stop, L to right, and so on. So I'm going to um, just to show that what we are getting on the odom topic. I'm going to move our total board. Okay, so I'm pressing I now. It goes forward. Okay, I'm pressing comma. It goes reverse. K to stop. Okay, now let's see. This is the odom topic. We have this pose, position, orientation, X, Y, Z, and W. So this is the information that we want. And the orientation, this is the values which represents the rotation or the mm, rotation angle of the robot with respect to the world. Okay, but X, Y, Z, and W, these are values in quaternions, um, not in the usual Euler angles that we human beings are more uh, used to, or more something that we can understand more intuitively. Okay, so before we can do anything about this, we have to convert quaternions into Euler angles first. Then only we can um start controlling the robot. And how to do that, I would direct you to this particular video, our an older video of ours, ROS Q&A number 44, on how to convert quaternions to Euler angles. This is a very good video to understand, what are quaternions, what are Euler angles, and how to convert between them from quaternions to Euler angle and Euler angles to quaternions, all in Python. And there is already um, a sample script here on how to do this. So I'm just going to copy this. Okay, so copy this, and I'm going to paste it in our IDE. But I've done this before, and what happens is, oh sorry, we need a new package before we can do anything. Okay, stop this. Alright, so let's go to our Captain workspace, source, to create a new package. Let's call it rotate robot. Put ROSPy as a dependency. Alright, cd into rotate robot. Make a new directory called scripts. Okay, so in our Captain workspace, the source, we have rotate robot, and under scripts, okay, create a new file. Let's call this simply main.py. Okay, so I'm going to paste um, the sample code just now from the video, from this video here. Of course, the link to the video will be in the description below. Alright, so let's see what's happening here. Let me zoom in a bit. So basically, it's importing ROSPy, it's importing odometry from nav messages, and some. These are the functions which we can use to convert between these two values, from Euler to quaternion. Sorry, from quaternion to Euler, or from Euler to quaternion. Okay, and this is just to initialize our three variables: roll, pitch, and yaw. These are the Euler values. We are, of course, as human beings, we understand this more, understand this better. What is yaw, what is pitch, and what is roll. So really, what we are interested in this particular um, uh, robot is the yaw. Okay, yaw is the heading or the turn to the left or to the right. Okay, Let's skip this and see that we are going to initialize a node called my quaternion to Euler. We are going to subscribe to odom, and any messages that we get from this particular topic, we are going to call get rotation, this particular function. So we are going to get quaternion from here, message.post orientation, store it in orientation Q, then get the list of X, Y, Z, and W, and from there we can find the roll, pitch, and yaw using this function, Euler from quaternion. Okay, so again, this is what we want. We want the yaw. So then we print the yaw. Um, it says here the rate will be 1. Okay, let's leave it for now. And then while not ROS5 is shut down, we okay, this is just to convert from Euler back to quaternion. Um, we don't need this. We don't want this. Let's just comment it out and then sleep. All right. So let's just save this and run. So the ROS run. Oh wait, we have to make the Python file executable first. So cd into scripts. Okay, that's our Python file. So chmod plus x and name of the file. This is to make the Python file executable. Then only we can do ROS run, our name of the package, and the name of the file. Main.py. Okay. Oops. Rotate. Sorry, our that's not our package. Name of our package is ROS run rotate robot main.py. Okay, so this is the value of yaw that we're getting, and remember this is in radians, not degrees. Okay, and this is with respect to the world coordinates. So um, 0 should be pointing that way in the x axis direction. Okay, and it will go positive, if I'm not mistaken. Yeah, positive to the left all the way around. Okay, so let's use this teleop twist keyboard node to control the robot and see. So right now it says the heading, the orientation is 2.4 radians. So let's go say to the right. Okay, stop there. Right. So it is pointing forwards now. This is towards the x axis. So we are getting about 0.03. Okay, which means 0 radians pointing forward. Let's say go to the right, and about there, about 90 degrees to the right, it is minus 1.5, which is half of pi. Okay, pi radians is 180 degrees. Okay, let's turn to the back. Let's face to the back. So now it's about minus 3.0. It's about pi. Okay, um, and if you go to say point directly to the left of the robot, it will be about 1.6. It's supposed to be about 1.57. Okay, so you get the idea. So this is our angle. This is coming from odom topic. Okay, this is what we are getting from odom, and we have converted um, the values that we get from odom topic, which are in quaternions, we have converted into Euler angles. And there are three, of course, there are three values, three different angles, roll, pitch, and yaw. But what we are printing is just the yaw. Okay, so now we are going to use this value to control our robot, to move our robot instead of using keyboard teleop. Okay, so Let me just stop this. Not that one. This one. Stop. Stop. Okay. So let's save this as a new file. Save as something else. I'll call it rotate.py. Okay. So ROS.init node, I'm going to change the name of the node to be rotate robot. Let me zoom in so that you can see clearer. Okay, so the name of the node is rotate robot. We are still subscribing to odom. We are going to publish to command val. So ROS.publisher, going to publish to /cmd_vel, which is of type twist, and queue size. That's one. Okay. In terms of the rate, of course, we are going to control the robot, so we want the rate to be much faster. 10 Hertz should be okay. Oh, of course, since we are going to use twist, we have to import. So from what is twist? So here, excuse me. Still can't see because I've zoomed in this now. Okay, so ROS topic info slash command. Okay, this is how we want to get more information about a particular topic. So for topic command val, it is of type geometry messages twist. Okay, so we have to from the geometry msts.msg import twist. Okay, then only we can use twist here. Alright, so we have set up the publisher, and then we will need a variable, I'll call it command, that will hold the value, the twist value. Okay, so then, so inside our loop, in our while loop, we have to give this command dot angular dot z equals to what? Okay, what is the speed, what is the velocity that we want the robot to rotate? Okay, and then we publish pub.publish command. Okay, so now our next task is to get this particular value. So we have the yaw, we know the angle, we know how to control the angular velocity of the robot. How do we link these two? Okay, I'm going to show the most basic way, the easiest way, I suppose, to do this. Okay, it might not be the best way, but it is the easiest way, and you should be able to understand this first before you start trying to do some more complicated or more efficient way. Okay, so let's just define one variable called target, and this is our target heading. Okay, we want the robot to rotate towards what heading. So I'm going to put, say, 90 here, 90, meaning 90 degrees. So the robot will always, once we run our code, the robot should point to 90 degrees yaw. Okay, so then what we're going to do here is we are going to calculate the difference. So from target minus the current yaw. Okay, this is the difference, and I'm going to use a simple proportional controller, or P controller. It's not PID, I'm just going to use P. So it's KP times the error, the difference, target minus your, whatever this value is, we'll feed it into command.angular.z so that the robot will rotate. So let's define KP. KP, let's put it say 0.5. This is a value that we will have to try to get the best number. Okay, so did you get that? So we are going to get the yaw value. What is the current heading of the robot? We have the target heading. Okay, the difference. Based on the difference, we are going to tell the robot to rotate. So if the difference is big, it will rotate faster. If the difference is small, meaning the robot has rotated, is already pointing towards the target, then the difference is going to go towards 0. So the velocity, the angular velocity will be 0. Okay, so let's try this. Let's save and go back to our shell. Zoom out. Oops. Okay, so again, first we have to chmod as x rotate. Okay, make our Python file to be executable. Then we can do ROS run, rotate, robot, uh, rotate. Okay, let's see our simulation. So right now, wait, it's already pointing to 90 degrees to the left. Oh yeah, one more thing. Okay, this target is in 90 degrees, whereas this yaw, the yaw value that we are getting, is in radians, right? So let's convert that. Um, let's put target rad equals to target times dot pi divided by 180. Yep. So this will convert the target. That's too much. This will convert the value in target from degrees angle into radian. Okay, so this will be target underscore radians. Okay, and we need to import method find. So just import math. Okay, what else? Okay, so this is printing yaw. I don't want it to print yaw there. I want it to print here. So print target equals to what, and current yaw equals to what. Dot comment target yaw target underscore red. Okay, this is just to print some numbers so that we can see. Okay, save all that, and let's try again. Okay, run. Wait, let's use this node to turn the robot away. Okay, that looks good. Okay, just looking somewhere else, not 90 degrees to the left. Okay, so now run this, run our Python code, and there you go. The robot is turning, and it will stop once it reach. So the target is 1.57. Currently it is at 1.57. So it has slowed down. Yeah, that looks good. Okay, so let's try a different value. So let's say the target now is, let's put minus 45, for example. Minus 45 degrees. Okay, save, and this is on. Run this again. So minus 45 should be somewhere here, pointing somewhere here. So robot turns and slows down once it's almost reached the point, and you can see that it is uh, it's actually still moving, just so slow. So yeah, now it is pointing to the same heading as the target. Okay, so let's just try, say, 270. Well, let's put some really weird numbers. 284. Oops, and stop this. Okay, run again. Oh, what happened there? It's way. The target is 4.95. That is beyond, I suppose, beyond the comprehension of the robot. Let's do, instead of 284, it should be what, 360 minus, no, 284 minus 360, so that we the range would be um, between minus 180 to 180. Okay, let's try this again. So the target is minus 1.3, and it is moving then. Okay, so there you have it. This is the basic idea of how to answer this particular question. Of course, um, as I mentioned, this is not the full answer. This is the basic idea of how we get the angles from odom topic and convert it into the command val topic. Okay, so that we can control our robot to point to a particular um, a, position or heading, to be more specific. Okay, so if you want to have if you want to understand better and have a better answer or better way to do it, to see a better way to do it, just go to our Robot Ignite Academy. Okay, go to our Robot Ignite Academy. In ROS Basics in 5 days, the first course that we offer. Let's load it for some time. Okay, if you go to unit number 3, services in ROS, which is part 2 of the services course. Okay, this is a more interesting and more complete answer. Okay, using a very interesting robot as well, using BB-8 robot. So what it's going to do, what you are going to do in this particular exercise is to make a service such that the BB-8 robot will be able to do to move in a square, like so. Okay, so the robot will go forward, and after some time, a specific time, it will turn 90 degrees and then go forward again, turn 90 degrees again, forward, turn 90 degrees, then go forwards, and so on and so forth. Okay, so have a look. This is a better answer, a more complete answer to do this. Um, and let's just see. The this is the expected output. Okay, the robot will go forward, turn, forward, turn, forward, turn, so that it moves in a square. Okay, so that was all. In the description of the video below, you will find all the links, all the resources that is mentioned in this particular video. So did you like the video? If you did, please give us a thumbs up and remember to subscribe to our channel and press the bell for a new video every day. Either you like it or not, please share your thoughts and questions in the comments area. Peace out.